So welcome everyone to our CCNP ENCORE class for the 6th of April. I want to share my screen and show y'all something that you may or may not be aware of. I mentioned it, but I want to mention it again just to be absolutely clear. If any of you need to renew your CCNA, you can actually do it once you complete this class and you finish successfully. So if you finish this class successfully, you can renew your CCNA for the next 3 years if it's active. Now it has to be an active CCNA. It can't be, it's not going to certify you a CCNA, but if you currently hold an active Cisco CCNA, this course will earn for you, sorry, my phone is making all kind of noises here. This is earning for you if you pass it up to, I think 64 credits. Yep, 64 CEUs. So this will allow you to, with your associate, you only need 30 credits in order to renew it for 3 years. So the process is very simple. You basically just go into ce.cisco.com once we finish the class. Now you can only do this when the class is over and you have been marked as complete and successful in the class. And then you'll go into submit items. You'll put in there that you took, in this case, we're showing DevNet Associate, but you will show your CCNP ENCORE, that it was a networking academy, and then you need to put the start and end dates, and that would be the dates that show in our NetAcad class. And so you can go into our NetAcad class and, I see that one's that one. Oh, okay, yeah, that was a different one. Good, scared me to death. That one. It's this one. Okay. So in our class on NetAcad, you will see under CCNP ENCORE that our start date was February 16th. Our end date is May 12th. So you put that in to the start and end dates, and it takes about 7 to 14 days, and then it will be either approved or denied. And it should be approved if as long as you've completed the class successfully. So if you are a current holder of a CCNA certification, this class easily will recertify you. If you're actually currently holding a professional certification, so you're a CCNP, this one class will not recertify you, unfortunately. You'd have to take this one. And right now, there's no, well, there is NARSI. So if you take this class with me this summer, you would get enough course or enough credits to renew your CCNP. All right, so I am offering CCNP Enterprise ENARSI is what it's called this summer. So if you take those two together, and you are already a CCNP, you can renew your CCNP for the next 3 years. So I just want to make you aware of that. I know I've mentioned it before, but I want to show it again just to make sure we're clear on that. All right. Now, my next item I want to go over is we're going to talk about first hop redundancy protocols, and we're going to bounce through the lab on first hop redundancy protocols. Turn my video off because it just takes up space on the screen. So first hop redundancy protocol is a key network resiliency component. The reason being, if we look at our normal networks, typically a host can only have a single default gateway. And for this reason, it's very difficult when you set up first hop redundancy to have the host have more than one. Now, there's actually a way using ICMP redirects and ICMP that the host can find another default gateway if its primary gateway fails. And there's even ways in some operating systems to set a secondary gateway. But we're going to look at a different way to solve it. We're going to solve it using a first hop redundancy protocol. We're going to talk about, in our case, multiples, but we're going to only get config for us today. We're going to config HSRP or hot standby routing protocol, redundancy protocol. And HSRP is a Cisco proprietary protocol. It is designed so that you can create a virtual gateway IP and a virtual MAC address, and that can be used so that you can put that on your host, and the host will never know whether it's going through R2 or R3. It will just see that it's going to a virtual IP address. VRRP is the open standard version, and it is very similar to HSRP. One of the differences with VRRP and HSRP is that VRRP can actually use as the virtual IP address, one of the IP address on the primary router that's being used or primary device. HSRP cannot. The IP address for your virtual router cannot be one assigned to a physical device. On VRRP, it can be. The other thing that is different between VRRP and HSRP is GLBP is a first hop redundancy protocol that is designed to let you do actual load balancing. So with VRRP and HSRP, the idea is still you're going to have two paths, but only be using one of those unless you do some. There's a way to do some kind of weird configuration with VRRP and HSRP so that, say, VLAN traffic for 10 would go out one side as the primary, and the other side would be the secondary, and then VLAN 20 would go out the one side, and then the other would be secondary. Kind of like we do with spanning tree when we set different spanning tree routes. It's a very similar concept. But by default, HSRP and VRRP are not designed to load balance across the links, but GLBP is. It does try to load balance. Now, one of the problems we will learn about as you're doing your reading and dealing with first hop redundancy protocols, what it typically does is it creates that virtual router in between there. So you see R2 and R3, we've got .2 and .3. So we would make 172.16.1.1 the virtual router. Well, HSRP will keep up with the status of R2 and R3's inside interfaces, but it does not by default keep up with the status of the external interfaces. So let's imagine that R2 is our active router in HSRP, but its WAN link fails. Well, unless you're tracking that WAN link and the status of that WAN link, it will have no effect on HSRP because R2 is still up on the 172.16.1.0 network. So this is why we have the ability to do what we call object tracking. And it can be, typically we do the status of a link or the status of a route, but this is when you're doing HSRP, you can say track one IP route to this reachability. So as long as it's reachable, then it would use HSRP and would use that particular route or that particular network. If it wasn't reachable, it would not. Here's a more common one where we do the interface. So on our previous item, we would actually track the status of the WAN links on R2 and R3, so that if the R2 WAN link died, then HSRP would automatically make R3, well, it would actually hold a quick election, but it would make R3 the active and start sending information through R3. So that is the purpose of tracking interfaces, so you can see the status of those. HSRP, minimum of 2 hosts. You can have more, but any other ones just sit there and don't really participate unless one of them goes down. There is an active and a standby. The active router receives and routes all the packets through a virtual IP and a virtual MAC address, like I mentioned before. If the active fails, then the standby becomes active and starts sending packets. Now, one of the weird little quirks of HSRP is that if the active router comes back online, by default, it will not become the active router again. So, for example, let's go back up here. Let's imagine that in our diagram right here, R2 is the active router, R3 is standby. R2 goes down, or the link breaks for some reason, so R3 becomes the active and R2 becomes the standby. We fix those issues on R2. R2 stays in standby mode by default. Now you can change that by a command called preemption or preempt. And if you do that, then R2 will preempt and become the active router or again, but by default, that is not enabled. We'll show you that in the lab. The other thing that HSRP can support is millisecond timer values so that you can have extremely fast switchovers. The only thing you have to be careful with these millisecond switchovers is be aware that you don't want to set your HSRP to be so fast that other things in your network, like routing protocols or the ability to route, can't handle the speed at which HSRP switches over. So if your HSRP switches over, but your routing's not working, well, then you're really not doing a whole lot for yourself. So how do we configure it? Well, you define an instance with standby and the IP address. You turn on preemption if you want to. You can change the priority. By default, the priority is 100. I believe it's 100 or 110. 110. Pretty sure that's right. And the higher is better in this. So if you have a higher priority, you will actually become the active router, especially if you have preempt. And then you also can configure the MAC address if you want to, but it is created by default. And then here's changing our timers, and you can do it in seconds or milliseconds, not micro, excuse me, milliseconds. The last item that's available in HSRP is the possibility of doing authentication. That is a good idea because that way you can't have someone bring in a router with a higher priority and just join in your HSRP group and take over the active route, active status. So let's go now up to NetLabs. And I have this lab loaded, okay? I haven't put any IP addresses on P1, P2 because I'm just probably gonna ignore them for this. But I'm gonna pop the content open here. I'm gonna undock it, put it right here. I'm gonna take this and I'm gonna put it over here. And let's see if I can't get my two items on the same. Okay, so I've already dropped in my default configs from our information, so I don't have to do that. All of this is up and running. So I'm going to go down here and we're going to, on switch D1, we're going to set up on interface VLAN 11 HSRP. So we're going to do it, by the way, with version 2 with a standby IP address of 10.11.0254 and a priority of 150. So I'm going to do this first, though, just so I want to check something. So let's go config T. Let's do int VLAN 11. We're going to do standby version 2. We're going to do standby 11 IP address of 10.11.0.254. We'll do I'm gonna hold off for a second on the priority. Standby 11 preempt. Okay. I'm going to do show standby. Okay. Default is 100, not 110. Sorry, default is 100. That's what I wanted to make sure. Okay, so the default is 100. So what we're going to do now then is we're going to do standby. What happens when I set the standby priority to 150? What does that do?
Higher is better.
Higher is better. So when we go to D2 and configure it in VLAN 11 to be part of this HSRP group, it's going to have the default priority of 100. So the active router should be D1 when we go in here and look. So now we're going to do it for IPv6 on this same VLAN. And because version 2 supports IPv6, we can easily just do IPv6 auto config. And then we can do standby 116 priority 150. Change that again for this one, and standby 116 preempt. So we're going to preempt it. Okay. Now we're also going to do the same thing for VLAN 21. So int VLAN 21 standby version 2 standby 21 IP 10.21.0.254. Standby 21 preempt. Standby 21. Okay. And then standby 216. 216. Oops. IPv6 auto config. And then standby 216. Notice we did not change the priority for the 216 group. So now if we do a do show standby brief, you will see that we are active VLAN 111. We have a virtual IP address of 10.11.0.254 that's being associated with VLAN 11. On VLAN 20, we have 10.21.0.254. And it was in the speak mode here, so it had not yet become active. But if we do the up arrow, we should be active for all four. So we're active for IPv4 on VLAN 11, IPv6, and IP4 and 6 on VLAN 21. So now we're going to go over to D2, because if you notice in our topology, D2 is going to be our other possible gateway out. So we're going to go to D2 and interface VLAN 11, standby version 2. Let's see, standby 11, 11 IP. It's going to be the exact same one, 10.11.0.254. And standby 11 preamp. You'll notice it's not going to become the active because it is not, it doesn't have a higher priority than 150. So IPv6 auto config, and then standby 116 preamp for that. Okay. You notice it even tells you that for group 11, VLAN 11, it went from speak to standby. So you can see it's talking. Here in a minute, we should see for VLAN group 116, it goes from speak to standby. And then we'll go interface. There it goes right there. Yep. Interface VLAN 21. Standby version, standby version 2. And that just allows us to support IPv6 and IPv4. That's why we're using version 2. Standby 21, IP 10.21.0.254. Now, notice what's going to happen here. Standby 21 priority 150. And then we're going to do standby 21 priority, preamp. Oops, we got to spell it right. Standby 21 priority 150, which I've already said. I'll do it again, just make sure I don't mess up. And then standby 21 preamp. Now watch what's going to happen now. Originally in 21, it said speak standby, but now we're going to go active because our priority on the 21 group is higher than D1's priority. And we use the preamp command, so D2 took over for that particular group. And we'll do the same for this. Standby 216 IPv6 auto config, and standby 216 priority 150, and then standby 216, gotta spell it right, 216 preamp. And what we should see is it may still go went straight speak active. Okay, so you'll notice that for this one it didn't do that because I got it in quick enough. So we now, if we do a do show standby, we should see that for group 11, D2 is in standby mode. The virtual IP address is 10.11.0.254. The active MAC address in the virtual MAC address, so there's the virtual MAC address that all hosts have in their tables. The priority is 150, okay, for the active router. Preemption is enabled. The priority for D2 on VLAN 11 is 100. So that is why D1 is currently the active router. Pretty much the same thing holds true for 116, group 116. Okay, so we're still, the active router is D1. We go down to VLAN 21 though, group 21. Now we can see that D2 is active and it's also active for the 216 group. So we can easily see that do show standby brief. We now have multiple different standby groups, and we had the ability for the groups to go in. Actually, I will real quickly do PC1's. Watch this. I'll do PC1's IP address real quick here, so we can do a ping command. All right, so let me change this because this is ridiculously big. I've got to get these fixed, folks. It's just one of them things I never have time and then when I get in here and remember it, PC1 Ethernet. Let's change your adapter settings. Now notice for this, we're going to set the default gateway. Oh, that's weird. Oh, wait a minute, hold on. I might be on the wrong one. I am on the wrong one. I need to be on the, remember, we're supposed to be on the bridged, not on this one, on the bridged. I was about to make that mistake. So we got to be on the bridge. So we're going to put our IP address in here, and we're going to put 10.11.0.50/24.255.255.255, and then 10.0.11.254, which is the virtual IP address we set up. Oop, what did I do wrong? Oh, 0, 10.11. Yeah, 10.11.0. All righty. I'm glad it kept me from making a stupid mistake. So now we'll close all those out. We go back to here. We're going to go, so it'll be clear, actual size. And we'll go IP config, and we should see, oops, there it is down there. So we're going to ping, first off, let's ping the virtual IP, 10.11.0.254. And we have pingage. So we can ping the IP address that's associated with that particular group. So we're going to now, we're going to start a continuous ping. So we're going to ping -t to 192.168.1.1, which is one of the loopback interfaces. Well, if I put the right thing in. And I, of course, did not. So let me go open a different one. So ping 192. I just want to check it first. 68.1.1. I just want to make sure it works. Yep, it works. So now we'll do a continuous ping. Ping -t 192.168.1.1. All right, so we've got continuous pingage. We're going to go, and we know for this particular one, so we'll go over here and we do a do show standby brief. We can see that we are active for on D1 for 10.11.0.254. Okay, and that's on interface VLAN 11. So we're going to go in here now to int VLAN 11. We're going to shut it down. Okay, so actually I'm going to pull, watch this, I'm going to undock this. So we're undock. So here's PC, it's just pinging away. Over here's D1, we're going to shut it down. Now you'll notice that it went down. We'll go over here to D2, do show standby brief. And you can see now this is the active for 10.11.0.254. You'll notice our pingages, we never even had a single drop. So it's just pinging away. Well, it's supposed to be. Okay, maybe it did drop. Oh, there it goes. So there was a pause. There was a slight pause as it picked up. It didn't time out, but it looked like there was a slight pause there. Now, the cool thing is, and one of the things I show you in the lab, and I'm not going to continue on this lab because I've got the basics of what I want you to see, but you can, that little bit of pause we had in there as it was trying to do the pingage and trying to stop the pings there, we can actually make that almost immediate by changing our timers to milliseconds instead of seconds. Because if you look, go back in here and close that PC. If you look in here, if you do an actual show standby, do show standby, that way I don't have to drop out. You'll see that for this group, you can see that the hello time is 3 seconds, the hold time is 10 seconds. So if there is an actual drop, which there was in this case, it can take up to 10 seconds for D2 to become active. But we can drop that down into the millisecond range, and then it's almost immediate. Okay. So there's very little traffic loss, but there was some. And if you go into these milliseconds, it can be almost no loss whatsoever. questions about HSRP? Now, the rest of this is just messing with the timers, setting up authentication, and also doing our object tracking. So you can actually look at the line protocol and look at the different items here. Now, this decrement, what this does is when the object fails, that causes the system priority to drop by that amount. So on interface VLAN 11, if the loopback interface went down, the line protocol went down, it would decrement the priority of 11 by 60, which would put it at 90. And since preemption is on, that's below D2's, D2 would take over. And then vice versa, it's done the same thing so that for VLAN 21, if the interface loopback goes down, then D2 would have a priority of 90, which would be less than the 150, or excuse me, less than the 100 on D1, and D1 would take over for D2. So that's how this standby track item works. You set up the items you want to track, and you tell it how much you want it to decrement the item. I believe, if I'm not mistaken, the decrement level by default is 20. So just be aware of that. So you need to make your priorities the right amount if you don't change the decrement time or decrement number. All right. Questions about HSRP? Okay, I'm going to end this reservation. Any questions before I end it?
I'm good.
Is that a yes or no? None?
I'm good.
Okay. So what I'm going to do now is I want to talk a little bit about, I'll actually close this one. I'll talk a little bit about GRE tunnels. Okay. GRE tunnels, or generic routing encapsulation tunnels, are used for a wide variety of things. They can be used to change the way that a link work, not a link, but the way that a connection between two different remote sites appears in terms of the number of hops away. You can actually put different protocols inside of GRE to form VPN tunnels. GRE is protocol 47, and what it does is it puts an entire new GRE header on top of the original packet, which is important because that means it's going to change the size of the MTU in a lot of cases, or cause problems in some cases with that MTU. But the original GRE header goes on here. We're going to create a tunnel, and actually I've already created a tunnel. In fact, here's what I've created. I have this created on our setup inside of Cisco Modeling Labs. I have 192.168.12.10 over here on this PC. This is 12.1, 10.001/30 and 2 between these R1, R2, 10.000.4/30 between R2, R3, and then 172.16 but on the R3 side. So this is the setup I have. Now, as part of that, okay, so we're looking at a tunnel here. As part of that, what I've done is I've also set up so that on PC1, if I'm in here and I do a trace route, you will see that to get from PC1 over to PC2, and that's this right here, it goes up now to 192.168.12.1. So it goes up to my default gateway on R1. The next hop is 10.0.0.2, which is the IP address on gig 00 of R2. The next hop is 10.0.0.6, which is the IP address on R3. And then it's finally delivered to 172.16.0.10. Vice versa, if I'm over here, you can see that if I ping 192.168.12.10, the reverse happens. I go to 72.16.0.1, 10.0.0.5, 10.0.0.1, and then 192.168.12.10. What we're going to attempt, and we're flying without a parachute here, we're going to attempt to create a tunnel from R1 to R3. And with that tunnel, we're going to force traffic destined from this network to that network and vice versa through the tunnel. And we're going to have it, hopefully what we'll see is that the hops change and everything changes. So when we're looking in here, the way to create a tunnel is you create the tunnel with the interface tunnel number. You tell it the tunnel source with IP address and interface ID. you do identify the remote destination IP address. Then you allocate the IP address you want inside the tunnel. Okay. Now you then can do things like bandwidth, keep alive, and defining the maximum ITU. So here's an example. It's a little hard to see, so I'm gonna zoom in on it. But here's an example of a tunnel. Interface tunnel 100, bandwidth they've set to 4,000. They put an IP address in for the tunnel. The tunnel source is gig 01, tunnel destination is this IP address, and they've set the MTUs and keep alives. Okay. Now, what you have to be real careful with, and one of the things they're going to talk about in GRE is you will get problems with overlay networks if you put the tunnel network into your routing protocol. We're going to solve that by using static routes to get across this tunnel. But be careful, because if you see in your syslog message anything about recursive routes and you're running a tunnel, especially a GRE tunnel, the most likely cause is because you have put the actual tunnel network into your routing protocol. So let's go back in here. We're going to go to R1. All right. We're going to create us a new tunnel. So we're going to go in here. We're going to global config. And we're going to do tunnel, interface tunnel, int tunnel. And let's do 100 also. Okay. We're going to do tunnel source. Now, there's a couple ways we could do this. We could do the IP address or the interface, but we're going to do interface. Okay, tunnel source. Yep, so we just got to do gigabit 0, 0. So we're going to do the outside interface right here. Okay. Now, our tunnel destination is actually going to be gig 01 on R3. So, oops. Tunnel destination is actually 10.0.0.6 because I know that IP address because I put it on there, but that's 10.0.0.6. Now you still have to have some way of getting to 10.0.0.6 inside of your routing table. I'm actually running OSPF on this network to make that happen. So I do have that ability to get there. Now I'm gonna do IP address, and I'm just gonna use for this one, let's use 131.107.0.1, 255.255.0.0. Actually, let's do /24.255.0. Okay. Now we're not going to change anything else on that. And then what I'm going to do is one more thing. I need to make a route. And so, well, let's do this first. Let's go to R3 and make our tunnel. Okay. So let's go in int, okay, config T. Interface tunnel 100, tunnel source gigabit 01, 0/1, tunnel destination 10.0.0.1, which I know is the outside IP address on R1, IP add 131.107.0.2, 255.255.255.0. Okay. Now, if I've done everything correctly, okay, now here's where I'm gonna get some trouble. And you're gonna see this in just a second. Because of the way I set up OSPF, OSPF is going to probably cause recursive routing problems for us. So let's get ready to see what happens here. So let's do a do ping 131.107.0.1 from R3. We got to ping it, so we're good there. Now let's try if we do a do show IP route. Right now, you'll see that to get from R3 over to the 192.168.12 network on R2, OSPF is being used for that. So what I'm actually going to do is I'm going to go exit, and I'm going to go IP route 192.168.12.0, 255.255.255.0. Next hop IP address is going to be 131.107.0.1. So I'm going to force that through the tunnel. I'm going to go back to R1. I'm going to do IP route to the 172.16.0.0 network, which is off of here. And I'm going to do 255.255.0.0. And I'm going to say 131.107.0.2. Okay. Do show IP route. We should see a static route to that 172.16. So now if I do a do ping to 172.16.0.1, success, 0.10, which is the PC, success. Now let's watch this though. Let's see the difference here. So we're going to 72.16.0.10. What should now happen is it's using the old route. Still using the old route. Nope, there it goes. That is correct. That's actually correct behavior there. Notice what it's doing. It goes from PC1 up to R1, and then it's now going through the tunnel. So before we had 4 hops, we took the R2 router out. Now the traffic between these two sides that's being forced through the tunnel with our static route is no longer seeing that R2 is even in the path. And there could actually be 30 routers in the middle, and they would have no idea that they're in the middle. And so they believe that R1 and R3 are directly connected to one another through this tunnel interface. Now we can do all kinds of stuff with this. We can route VPN IPsec tunnels through it. We can take and change the routing path through a network. We can even, in many cases, take different protocols and route them inside of a GRE tunnel so that IPv6 can be routed, or you can do things that you can just do all different types of things with a GRE tunnel. But the important thing to note is it really wasn't that hard to do. We literally just set up a tunnel interface. Okay. So we get in here and we set up the tunnel interface, and we gave it a tunnel source, a tunnel destination. And by the way, that IP address though has to be reachable somehow. Just so happens in our case, it was reachable via OSPF because we set up OSPF on this network. And then we give it an IP address, and that will set our tunnels up. And now R1 and R3 believe they're directly connected to one another through that tunnel. So if we do a we know do show IP route. Oops. You will see that because of those static routes, we believe that we are directly connected via the 131.107.0.1, or excuse me, we got via one hop away. We've got access to 192.168.12 network. So that is a simple example of a GRE, generic routing encapsulation tunnel, and its use, showing you how it can change the hops. Questions about that? Questions about GRE?
I'm good.
Okay. Now, one of the things I really liked is you'll notice that I do have CML up and working. So this is a lab that I created in CML, and it worked perfectly. So one of the things I've also learned is how to get into the console and the PC. So it's much easier now just to put an IP address on these little PCs and make them go using Linux commands. But we're gonna start, once I get the NetLabs pod set up for this, we'll start integrating some of this into letting you play with it if you want to. It's optional. You don't have to, because you still have access to our NetLabs full ENCORE pods. But if you want to play with this, it'll be a tool that you can play with. Okay. Any other questions?
I don't have any.
Okay, that's all I've got for today, folks. I want you to keep working.
One question, Kelly, for me.
Yeah, go ahead.
Security
Okay.
through the tunnel.
Say again.
Security through the tunnel.
Okay. Yep. If to do that, you have to change your tunnel mode. and then there's a couple ways you can do it now. And when we talk about security in the tunnel, by default, GRE has no security. All it does, if you'll notice, go ahead, sharing my screen. All it does by default is put a new header on top of the existing data. So there's no security. But there
Okay.
is another mode, okay? By default, we're just using GRE, but you can actually run IPsec inside of GRE tunnel. And that's actually part of the next concept that you'll read about in the book and pay attention to. But you can actually run IPsec inside the GRE tunnel, or you can take GRE and run it inside of an IPsec tunnel. So it's possible to do either of those. Now, the thing is, though, by default, I'm trying to find if there's anything that shows that on here. This is all Ike and ISACamp. Yeah, we know that. Where is it? Don't know if this particular class gets into it. I know we get into it, and we used to get into it in the old network security class. No, this one, yeah, here it is. I think it is. Yeah. So here is an example of, they basically are using a tunnel interface and they're enabling IPsec or GRE over IPsec. So by itself alone, no, GRE has no security, but you run GRE over IPsec, or you run IPsec inside of GRE, and that's how you provide your security. Does that make sense? So if you look here, you've got a tunnel interface, okay, but that tunnel interface is then being used for the for IPsec to run over. So it's GRE over IPsec with a pre-shared key. So your GRE is running through the IPsec. You can do it the other way. You can actually run IPsec through GRE. But be very careful. If you do just GRE, there's no security. It is, it's just a new header is placed on it, and that's it. There's no encryption. There's nothing there. Does that help? Does that make sense?
Yes, very good. Thank you, Kelly.
Okay. All righty. Well, I'm gonna stop the recording.